By leveraging reinforcement learning, we can revolutionize many of the industrial tasks done by much more expensive robots. We're reducing costs in hardware and putting that into software. You are not running a single simulation at a time. You are probably running hundreds, thousands of simulations at a time. I think there's a limit to what we can learn from data. We need to first think about the difference between data, information, and knowledge.
Hello everyone and welcome to a new episode of AI Without Borders. I'm thrilled to have Fabio Ramos. Fabio is currently a principal research scientist at NVIDIA focused on robotics and simulations and has co-authored over 300 papers which have been cited over 14,000 times. But most importantly for this podcast, Fabio was born and raised in Brazil. Fabio, welcome. It's great to have you here.
Thank you so much for the invitation. I'm super glad to be here.
So maybe starting from the beginning, what sparked your initial interest in robotics and AI, and how did that path lead you to move to USA and become a principal research scientist at NVIDIA?
Yeah, my history has been somewhat interesting and connected also to my family. I study mechatronics engineering in Brazil. At the University of São Paulo, and my father is also a professor at that university in electrical engineering. So when I started university, it was okay. Let me do mechatronics because I was always keen to, study engineering, but also see things operating in the real world, right? A very interesting scheme that Brazil has is to allow undergraduate students to do 1 year kind of internships with faculty at university to do research projects, right? And I joined one of them with a professor there. His name is Fabio Ramos, who was just arrived from CMU, from Carnegie Mellon University. He was starting his position there. And then that initial contact, I think I was maybe in the second year of engineering, basically changed my career, right? Because I realized why I was studying, linear algebra, calculus, physics, complex calculus, and all these things. There was I could see a purpose, right? I could see real applications of these things in research, right? Then when I was about to finish, Fabio was also working with a company called Hewlett-Packard, right? And at that time, so that was kind of late 1990s, there was this initial kind of wave of AI happening, right? Your perhaps older listeners might remember there was Microsoft was developing something called Clippy. It was this little agent who would help diagnose problems with your printer, for example. Clippy was based on something we call Bayesian networks, right? So it was kind of a statistical model based on probability theory that tried to have some reason and try to diagnose things for you. And I decided to work in that area, right? Probabilistic inference. And then I worked with Fabio, got my master's there. And then I was keen to, expand my horizons and work on robotics after working a lot on AI. And I ended up in Australia. Australia is very big as a country. The land is very large. And they needed a lot of automation. So if I wanted to do something big in what is called field robotics, so this is robotics that happens outside. So I'm talking about submarines, mining trucks, aerial vehicles. Australia would be perhaps the best location. And then I did my PhD there, ended up becoming a professor. And then I came to the US for my sabbatical, but we can get more into this later.
No, that's a great overview. And now that you mentioned that last portion, you are in a unique position of being both in the academia and industry. How do the priorities differ when doing research for NVIDIA versus when you're doing research on the university research front?
Yeah. So it was interesting because until 2018, when I joined NVIDIA, my exposure to, let's say, industrial research was basically a long time ago when I was working with Hewlett-Packard, right? I think what happened at that time, 2018, with NVIDIA was really one of the first major players who believed that robotics would be a big thing in the future, right? So basically, Jensen's vision that robotics really could become a major area for development. So when I started at NVIDIA, I was a full professor in Sydney, and I was about to take a sabbatical for 1 year. And when I come to NVIDIA, I realize that the scale of things is very different than what happens at the university, right? At the university, as a professor, you run a lab. It's kind of a startup in a sense. You write grants, you get students to do research with you, and usually do things at a smaller scale. Maybe projects involve maybe 3 people, yourself, maybe another collaborator, and a student, and you perhaps have to narrow that down to a specific area of robotics. So let's say you pick perception, right? So you work on mapping, how to represent objects in the real world, and so on. At NVIDIA, we essentially started a new lab, a new robotics lab with 25 people. And we had a lot of resources, right, from the hardware perspective, robots to compute, all the GPUs. So essentially, the scale in which you can do things is very different. At the same time, you want to be able to deliver things, right? There is the research to product translation is very important in industrial research. And at the university, you can stay at the level of, let's say, fundamental research, right? So I think these are the main differences between the two, right? While at the university, we are mostly at the fundamental level research. In places in industrial research, you want to have an impact that goes beyond your papers. You want to have an impact that goes into products, that go into making others use robotics and so on.
Now it seems like you found the dream mix between both. At a broad level, can you share for the audience what's your current area of research or focus within NVIDIA?
Yeah. So NVIDIA essentially started in the area of robotics with a very simple mission. And the mission was, how do we make other companies to become robotics companies, right? How do we popularize robotics? And the idea is very simple. If we popularize robotics, we have more robots, more use of robots. You drive the demand for compute, right? And basically, NVIDIA is, it's a platform company. It provides the entire software stack and hardware for this, but I think more recently we are calling ourselves an infrastructure company, right? So other companies can build their things on NVIDIA's infrastructure. So when we started that, we realized that, well, what are the main bottlenecks in robotics at that time? Perhaps the most fundamental one was cost. Robotics was very expensive, right? Because if you want to run an experiment, you need to buy the hardware, put all the software, spend your time developing the software stack. And then you have a lot of time you need to put into maintaining that hardware, make sure it works. If it breaks, there's someone to fix it. Sensors need to be calibrated. There's a lot of effort that goes into that. And we said, well, if we are in a company that have been developing simulators for gaming for a while, right, and has that history of developing games, and those games do have physics engines on them, right? Why don't we create simulators that would help people creating their own little robot in simulation, running the full software stack in simulation before they can deploy into the real world? So my first goal was trying to help create good simulators that would scale using standard type of GPUs, and understand when simulators do not work or do not correspond directly to reality. What are the sources of it, right? What can we do to improve the simulation quality?
No, that's a great segue to my next question, which is reading your papers and following your research. You can see you've been doing a lot of work around simulation for a long time, going back even to your time in Australia in the mining space. I'm curious from your experience if you can share how has the simulation space been evolving, and what would you say is the current state of simulation research today?
Yeah. So the kind of simulations I was working on in Australia very different than what I was working here. So for a bit of context, in Australia I was working mining automation. So imagine, 250-ton trucks moving minerals from a place to another in an open pit mine. Most likely iron mines. These were the mines we were developing, right? So we were simulating the trucks, but more than that, we were simulating geology, right? What's underneath the ground? A lot of the mining processes work by trying to estimate what you have down in the ground. It's very different than, a warehouse. You can count things. In a mine, you have no idea, right? So you can only sense from the top and you have to estimate. So it's a big statistical problem. So the type of simulations we were doing was trying to recreate what we think the minerals were at that time, their locations, the concentrations, and things like that, and then use the simulation to optimize the process of extracting that. So putting excavators there to remove the iron ore and load them into trucks. So it's a very different scale, and a lot of that rely on clusters of computers, lots of CPUs, and so on. What is happening now is, as I move to NVIDIA, and we are mostly interested in more general robotics, let's say, right? So manipulators, robots that can help you, let's say cooking, doing tasks like cooking or cleaning a table and things like that. We didn't actually need that level of scale in terms of space. But we needed to model other things, particularly things that related to grasping objects, manipulating objects, this dexterous manipulation, as we like to call. And that requires a lot of modeling of contacts, right? How surfaces get in contact with others, and then frictions and restitution coefficients, all of these things are very complicated. So what happens today is we have simulators that first, you are not running a single simulation at a time. You are probably running hundreds, thousands of simulations at a time. And each of these simulations has a slightly different parameterization than the other. So we are not talking about a simulation. We're talking about simulations in parallel. And we hope that reality is somewhere in this set of simulations, right? So what I think is a great summary of what simulation is today is the fact that you can simulate many realities at the same time. And your robot can learn not just based on one reality, but based on thousands of realities at the same time.
Now, I find this topic fascinating. I have a lot of questions, but maybe starting from one of those parts. So one of the key parts on simulation and the research you've been doing is the importance of accounting for uncertainty and considering, as you were mentioning, the amount of multiple possible scenarios you can have. One of your research that I was reading was about probabilistic inference, and I thought it would be a good opportunity if you can maybe share a little bit more about it and how has it changed the approach in the way that we do simulation, and a little bit of how that contrasts with older methods.
Yeah. So probabilistic inference, since the very beginning, was one of my key areas, right? I was very interested in the methods for doing probabilistic inference. And I had to apply that a lot in these mining problems, right? Not just because, the trucks are pretty heavy. We don't want to see accidents, right? And also to infer the quantities down, in the ground is a statistical problem. You want to assess how certain you are about the mineral concentration, how wrong you might be, and so on. So I was always interested in not just estimating my best guess, but how wrong I might be about something I was trying to estimate. And also this, what is called the long tails, right? So, events that are unlikely to happen, but when they happen, they are pretty problematic, right? So like trucks running into cars and things like that. So this was part of my, there's always been part of my research. But when I started at NVIDIA and incorporating now simulation, right? I thought that I could use this same kind of reasoning to think about simulators as an inverse problem, right? So if you observe reality and the reality does not correspond to what the simulation says it would. How can you change the parameterization? What's the distribution, probability distribution over simulation parameters that somehow would make things agree to each other, right? So this is known as an inverse type of problem, right? So you go from observations to inferring these variables, right? To put probability distributions on these variables, and that allows us to basically build simulators that better represent reality, or at least they would know when they could be wrong. I think that is one of the main points of it, right? We now have simulators that could know that they are wrong, and then you say, well, if I'm simulating in this part of the totally confident of that, so I should be more careful with the answers, right? And since you have a simulation that is not totally confident, everything else kind of follow through. So when you are doing state estimation, for example, you can take that into account. If you are doing planning or control, you can take actions that will kind of try to minimize potential problems, right? The worst case scenarios, for example, right? So everything kind of fits into place when we start the process with uncertain or probabilistic simulation.
And one of the things that caught my attention was when you previously mentioned the importance of also understanding when simulation does not work. And I wanted to ask you about it. If there are some common causes, either common causes that you have identified that apply more broadly, or maybe use cases when you simulate, it tends to have more errors than others.
Yeah, that's an interesting and timely question. I'm writing an article. It now has 30-something pages just on what we call the reality gap, right? Is the gap between simulation and the real world. And there are many causes of it, right? So the most, let's say, easy to understand causes are related to modeling. So we are modeling aspects of the physical world. And models are useful. We hope the models are useful, but they are approximations of what happens in the real world, right? So you can imagine, for example, if you are modeling fluid dynamics, right? So there is an equation that describes fluid dynamics called Navier-Stokes equation, and that equation has many, many terms, right? And sometimes you tweak that term, or you don't use that term, you make the simulation faster, but you lose accuracy and so on. And I think when we look at simulations for robotics, we need to address that point, right? So it's accuracy. If you want something that is super accurate, it might be much slower to run. You cannot run as many instances in parallel as you could, and so on. So there is a trade-off in there. But the sources of this reality gap are, for example, the modeling components. There are aspects of the nature of the process. So if something is of a chaotic nature, for example, right? Some processes, particularly related to fluids, have a chaotic nature. Depending on the initial state of the system, it might evolve to unpredictable ways. There might be stochasticity. Also, when you measure things in reality, you might measure something that, what you are measuring is an approximation of what the reality is, right? So, what's the temperature in the room? It might give you, 80 something degrees Fahrenheit, but in reality, 79. So there is a little gap in there, right? So that this comes into the stochasticity of your measuring process, right? But it's also the problem of dynamics. There are many things in robotics that require dynamics. What's the friction coefficient of that surface? What's the restitution? So when you compress something, how much energy you get back from it? And these are dynamics parameters are difficult to estimate unless you do like full-on experiments that might take a long time, right? This is just a summary. So if your listeners are interested, I can point you to this 30-page plus article.
We'll definitely include you in the description section for everyone. And there's one question that I had, which is, what's your personal view between this future view on like more humanoid, horizontal, do-it-all robotics versus more specialized robotics?
Yeah. Humanoids are pretty popular today, right? I think there's a lot of investment in humanoids, and I think they have an important role to play in our field. There's a lot of startups and so on. But it's not the only robot that we want to address here. In fact, I think the most popular robot we have out there is a robot that is manually controlled, and we see in almost any construction site, right? It's called the excavator. It's a big arm that digs and moves stuff, dirt around, and it's operated usually by a very skilled operator because dealing with these deformables, right, the dirt and so on, is actually pretty complicated. But it is a robot, right? There are actuators, there are sensors, there's some kind of feedback that goes into the operator. It moves around. So it's another instance of a robot. The autonomous cars, the trucks, they're all interesting robots. Now, what's my take between humanoid robots and others? I would say whenever we want something at home on unmodified environments that we live on, if we have something that has the shape of a person, it might be more useful in that. I wasn't much of that opinion until recently because humanoids were very expensive and difficult to build and maintain, particularly, the locomotion part, getting the dynamics of, going up stairs, downstairs, and so on. But in the last 2 or 3 years, the development of hardware and software for humanoid robotics has been just incredible, right? So you can buy a humanoid for, I don't know, maybe $20,000, $30,000 these days, that can go up, downstairs, can run, can jump, all of that. In terms of manipulation, they are still not quite there, but in terms of locomotion, they are very capable. It's very impressive to see that. I was in a conference last week, and there was a humanoid robot there that we could punch and kick. The humanoid would fall and would stand up back again in a few seconds. And I thought, oh, you kick a humanoid, you'll be broken. No,
Yeah.
anyone could go and kick them. So it was very interesting to see how much we have evolved in humanoids. But they are not the full solution to that, but they are certainly going to be part of it.
No, I imagine, and as it relates to your field of work, that the one thing that I have in mind as you have those more humanoid use cases is the challenge that likely you have to account for all the different possible, as you were mentioning earlier, edge cases, which again is the part that I don't know if the correct word is struggle with, but think it likely it's very, very challenging.
Yeah, that's right. And it's interesting that even though we can do very capable motions with these humanoids, something that we do so easily. So, for example, you want to slice a potato with a knife, right? We can do it without much difficulty, right? You try to do that with a humanoid, it's very hard, right? So we are still, there's a lot of research going on this part, right? The dexterous manipulation, contacts, the tactile process that happens when you touch something. These are things that humans do so well, and it's so difficult to do with robots in general and humanoids. We just started now on a journey to have more dexterous manipulation as kind of a main part of robotics research. We thought we could do most of the tasks using kind of pinch style gripper or parallel grippers, as we say. Now with dexterous, we hope we can do other things, right? So, for example, opening a bottle with a bottle opener. Humans can do that fairly easily, right? You try to do that with a humanoid, it's going to take many years until we are able to do this competently and generalizing to different types of bottles, bottle openers, and so on.
No, it's super interesting to learn the amount of small things that you don't think on a daily basis that are so easy, but at the same time so hard to get. One of the key things in robotics is data, and I wanted to ask your opinion about what you think about the kind of the hierarchy of robotics data as it relates to embodied data collection, video data, simulation generated data. Likely it's a combination of all, but do you think one of them will have more weight in taking us kind of to that next level in robotics?
So what is happening today is we in the robotics community, we are trying to leverage as much as we can the large language models or the vision language models and build out of them what is called vision language action models, right? So these are kind of LLMs that would output action. So control outputs for the robots, right? Where this gripper should go and so on. What we realized is that one way to address this hierarchy is to separate this model into two. So there's one model that is, let's say, the higher level. The reasons about he's the object I need to manipulate. He is the grasping for that object. This is how I should grasp that object. This is the sequence of actions, high-level actions I should perform. And then we have a lower level that essentially output trajectories. This is how my hand should move to grasp that object. This is how my hand should move to open that cabinet. This is how my hand should move to grasp this object and put it inside the cabinet and so on. So there was that kind of the composition, right? And most of these models would be trained based on proprioceptive sensors. So, the joints of the robotic arm, their positions and velocities. Also vision. So we would usually put cameras on the wrist of the arm and a camera that somewhat films the scene. So it has a broader view of that. I like also point clouds. So it's not expensive today to have depth camera. So it gives you the depth information as point clouds that you can embed it there, so you have a better geometry of the scene, right? And then we try to learn these models based on this data. But as you can tell, because we require all of these sensor modalities, it's difficult to download this data out there, right? So it's not that you go to Hugging Face and you're going to have thousands and thousands of data sets for you to download. This data is much scarce than what you get for LLMs. It's just text or vision. There are plenty of vision and YouTube videos and so on. You can download all of this. Robotics is difficult. So for that reason, we started to create data sets in simulation, right? So we have kind of simulation pipelines that a robot solves a task in simulation, and then we log all of this information, all the different cameras, depth, and so on, segmentation. So we actually pass segmentation masks. So each set of pixels, we give it a label, and your algorithm will know that this corresponds to a phone, this corresponds to a cup, and so on. And we make it available in Hugging Face, right? So I think that's one of the things, right? We want to build large data sets that everyone can use. And in the same way, universities and some industry labs are also putting large data sets on Hugging Face and other vehicles for people to download. So the amount of data out there is growing in robotics, right? But I think, to the other part of your question, right? I think there's a limit to what we can learn from data, right? And that is my personal take on this. I think data, we need to first think about the difference between data, information, and knowledge. These are three different things. So it's not because you have a larger data set that you necessarily have more information, because you might have data that is redundant. And it's not because you have more information that you can extract more knowledge from it, because it might be information that is just not relevant to what you are trying to do, or information that might be wrong in one way or another, right? So I think what I really would like to see are models that you can teach not just by inputting a lot of data and running back propagation, learning algorithms, but models where you write it down an algorithm on a board and say, now you follow this algorithm if you want to solve that particular task. Or here's a book, and this, chapter 3 is about motion planning. Learn that for me and output your actions based on this algorithm you're just reading from the book. I think this is the, getting knowledge directly from knowledge that we know and represent as language beyond just, inputting data to the models will be the next frontier for us.
And likely related a lot to this point, but one of the things I wanted to ask you is, what do you think is the path to getting to more kind of systems to thinking of robots that truly reason about what's happening there in the environment?
Yeah, a lot of what is happening now with LLMs are based on, a model called a transformer model, right? So these are types of neural network with a special kind of attention mechanism, and they are very good at retrieving data. So if you have data that looks like what you are seeing now, these algorithms, these networks, these neural networks are great in terms of giving you something that is very similar to what you observed in the past. But the field of artificial intelligence is much older than what we are doing with, let's say, machine learning, right? There are a lot of what is called reasoning methods, right? So, for example, a very popular method is called Monte Carlo tree search. So you build a problem in terms of a sequence of dependencies on a graph. So if you are in this stage, these are the possible outcomes. If you are in this stage, these are the possible outcomes, and so on. And you have effective algorithms that do this kind of search in these large potential trees that essentially are trying to solve reasoning. It's like what we do in our brain. If I do this, this will probably happen. If I follow that, this will probably happen, and so on. And you create these multiple scenarios, and then you take your actions, and so on, when you have time. Right, and sometimes they do that unconsciously, right? Just by remembering some of the events in the past, and this kind of reasoning is what I think would be very interesting to have together with database reasoning, right? Machine learning models, right? So how can we incorporate search algorithms, planning, task and motion planning methods that leverage optimization at its core as part of VLM? Maybe we would need to call it something else, but reasoning models, right, that incorporate data, knowledge, and reasoning methods for their outputs.
No, that's a super interesting part. And one of the things that we've been speaking a lot about is the simulation and the data. But to enable all of this, there is like the hardware on the back, for example, to be able to run those multiple scenarios at the same time. So I did wanted to ask you a little bit about how has the progress in the field, and NVIDIA being that at the forefront, obviously, of the GPU market, has been enabling a lot of the progress we've been seeing maybe in the past couple of years in the whole simulation and also robotic space, kind of what role that has played as well.
Yeah. So we like to decompose the hardware part of the problem into three main components, right? So there's a set of hardware or clustered type of machines that are responsible for training. So this will do all the very large scale training. I'm talking about the, Blackwell type of large GPUs, right? And large clusters on this. They're very efficient in inference and training. Training essentially means it's a statistical problem in which you try to estimate parameters of these very large neural networks based on observations, right? And that requires going over the data multiple times, right? I like to say we go over the data many times, kind of torturing the data until it confesses, right? And that's when we know the algorithm is done, the training is done. Then the second part of it is the simulation process. So if you train a model and then you deploy the model, and you would like to see all the renderings, you would like to simulate all the vision aspects, contacts, and so on. There is another type of hardware that is good for it, right? So the second part of the hardware setup is the simulation type of GPUs. They are very good at outputting images, generating images. They are mostly based on ray tracing and other technologies, right? They're efficient for this. And then finally, there is the machine that is next to the robot, right? The edge computing machine. These are the little Jetsons. They are perhaps they consume maybe 150 watts or something of that order, and they can run these neural networks, right? Or small versions of it, not at the same level, obviously, as the large GPUs, but they can take care of the motion planning, for example. They can do inference on diffusion models to generate the motions and so on. So these kind of three layers are the layers that we like to organize our hardware, right? In the same way, software is somewhat decomposed into these three components. There's a lot of research on the first one I mentioned, right? So training. I think we should do more on the little hardware, right? These things that actually do the real-time interaction with sensors and so on. They are super important, and I think we should devote more resources to that level as well.
No, it's been super interesting to see how kind of the progress from different directions, the simulation, the hardware is kind of all coming together to finally see the progress that we've been seeing. On the investor front, one of the things I've been hearing startups pitching me about is kind of applying the same principles about that they're used, for example, in autonomous driving simulation now for agent simulations. For example, simulating scenarios where a user asks an AI agent to plan a trip to France with their family for next year. I wanted to get your take on what's your take on those analogies. Do you think they apply? If yes, to what degree?
Yeah, one thing to remember with when you try to deploy the systems is you're probably going to spend 80% of your development time to address the final 5% of accuracy you need, right? It's all about the details, right? So as you mentioned in the autonomous driving car, I remember in 2008 there was the DARPA Grand Challenge in a city, and cars were there driving autonomously. There was one little crash, but apart from that, they were driving autonomously in that city. But that city had no humans. It was only the autonomous vehicles interacting with each other and so on. And it took us, I don't know, 15 years plus to go from that level to autonomous taxis, right? To Waymo level type of autonomy, right? With billions and billions of dollars of investment. When it comes to agentic AI and the use of simulation, simulation can be very helpful in a sense that first you should already know the basic principles of your process, right? The dynamics of that, from booking trips to any kind of software development or something like that. You should have some idea, but you should create a simulator to do the tough cases for you, right? So I think one of the main uses of simulation is what's the worst that could happen? How do I simulate a person that is kind of adversarial, has an adversarial behavior to what I want to see happening, right? And if you have a simulator that can generate these things automatically, that is probably going to be even more impactful than the agentic AI itself, right? The term for that application, right? Because then it's when you can look for robustness, reliability, and so on, which are the main bottlenecks in my opinion, right? So it's the last 5% of accuracy, of reliability that we are after.
Yeah, no, and that's why we see across the board. On the flip side, I've heard somebody saying that the only good part, as you make that analogy, is in self-driving cars, the risk that you can take are lower. Meaning, like if there's an accident, somebody can die. I'm gonna put you a little bit now on the spot on this one, but given that people have kind of different time frames about the expected rate of progress we're gonna see in this space, I wanted to ask you kind of how you imagine the state of robotics in 5 to 10 years. What do you think or hope and expect to see? And kind of what new capabilities do you think robots will have within the next 5 to 10 years that they lack today?
Yeah, right. So one thing that has been happening in the last few years, and particularly this year, is that robotics is becoming cheaper. The barrier to entry this area of development is getting cheaper and more accessible, not just the hardware, but software as well. As an example, there is this initiative called Le Robot, right, where essentially put everything on open source, from the robot itself, which you can buy kits with little servos for maybe $300, $400. And then on top of that, all the software infrastructure. So even people not familiar with robotics, but slightly familiar with, let's say, Python, a programming language, and a little bit of development tools like GitHub, you're able to collect your own data, deploy the robot. You might not understand what planning is, motion planning and all these things, but you can learn little policies that can, for example, put Lego blocks into dishes and things like that, right? So because this barrier is getting smaller and smaller, robotics is becoming more popular. The community is growing a lot. And with more people joining the community, the research community and development community, right, in academia and industry, the amount of progress that can happen is very difficult to predict. I'm still going to try to do my prediction here. Bury me for a second. But the first point is robotics is getting cheaper, right? And one of the things I've seen, so it's a work done at NVIDIA with some of my colleagues, was if you have an industrial problem, so let's say you are trying to put a nut on a bolt, right? So you're assembling something. That requires some precision, right? It's metal against metal. And you need kind of millimeter precision to do that. Can you do that with cheaper robots that don't have the level of precision by leveraging artificial intelligence, by leveraging machine learning? So one thing that we've done is to show that through a set of methods called reinforcement learning methods, right? So it's by reward and training simulation, we can take a relatively inexpensive robot arm and have it to perform that operation reliably, right? And when it fails, it tries it again. So it's not that we are specifically programming the robot to do exactly that motion to that level of accuracy. It learns automatically how to search for the area given its own inaccuracies to put a nut on a bolt and other tasks as complicated. Put a little gearbox together and so on. So that's the other component, right? So by leveraging machine learning, by leveraging reinforcement learning, we can revolutionize many of the industrial tasks done by much more expensive robots that have millimeter accuracy. So you're turning costs in hardware, reducing costs in hardware and putting that into software, into that type of development. So with these things in mind, right? So robots getting cheaper, leveraging machine learning, and so on. I think we will see in the future is the development of dexterous manipulation. I think is where the community seems to be going now, right? So how do we, for humans, it's so easy. For us, it's really difficult. How do we unpeel a fruit, for example? How do we have a robot that can feed people that had strokes, for example, right? They are problems with motion, grasping forks and knives. Can we have a robot that has that level of dexterity to handle deformables like food? Can we have robots that could fold clothes for you, right? Getting them out of the washing machine and so on. And in a sense, we can already have some of this, but not at the accuracy and robustness that require, right, for tasks that are more let's say, professional. But I would say if we can have robots that are under $10,000 and can do some of these housing tasks, right, cleaning, perhaps navigating safely in a floor, picking up a vacuum cleaner and vacuum for us, and helping in the kitchen, grasping ingredients and giving it to us, right? But more importantly, helping with people with disabilities, for example, or the elderly population. I think that's an area, right? So addressing the major demographic problem we're going to have with the aging population we have, not just here in the US, but you see even in China that is happening, obviously in Japan and other parts of Europe. Addressing these challenges will be, I think, what I would like to see in the next 15 years, right? Reliable robots that I could, put it there in a hospital or in a house with an elderly person, and I would be confident that the robot would help that person during that particular period of time.
And maybe one rephrasing that I wanted to ask you there, and let's use more the 5 time frame, as I think 10, it's so long in the space to make that prediction. But is there any one area that you think within 5 years, we will still have not been able to solve, likely, given the level of complexity within the kind of robotic sphere?
We're still not able to solve. Well, I think it's hard to predict, but if there is one area that I think we are still at the beginning, right, is the area of touch, contacts for very fine manipulation. And if that involves deformables, you'll be even trickier. So let's say a robot that could cut your hair, right? So it has to hold your hair, maneuver to under action, have all level of the dexterity to cut it without obviously hurting you and so on, and do these motions that are kind of smooth and reliably. That is extremely difficult, right? So if there is an area I think you'll take much longer to develop is this one. Other things like opening cabinets, doors, or putting nuts and bolts and things like that, I think those are much easier. We should be able to nail them in the next few years, right? But when we are dealing with deformables and contacts with the variables, and these things will take much longer, in my opinion. Yeah.
And we haven't touched a lot about this, and I would love to, given your background and the nature of the podcast, about the state of research in Latin America. And I wanted to get your view on what is your take on both the current state of talent and research in the field of robotics and simulation in Latin America, especially. I know you're particularly close with the Brazilian ecosystem.
Yeah, it's this is interesting because I think there's a lot of talent in Latin America, right? I had a number of students from Brazil, Argentina, Chile, Venezuela, Mexico, and what I find is that when they come with a very strong math background, physics, so all the foundations are there. They might not be super familiar with, kind of the latest things or the AI components, but it's relatively easy to teach them that if they have solid foundations, right? So I think what we are perhaps missing a bit in Latin America is that level. How do we take that pretty solid foundation you found in the top universities and turn that into research that is competitive, right, with others? I'm more familiar with what is happening in Brazil as I regularly go back there and talk to my friends and colleagues at Brazilian universities. And one thing that is obviously always a question is funding and consistency of funding, right? So in Brazil, at least, you have funding from research coming from basically three sources, right? So you have the federal government funding, you have the state government funding, and then you have kind of VC style funding or industry funding to startups. But what has been working very well for the state of São Paulo, so that's a model just for the state of São Paulo, is that the funding agency there is called FAPESP. FAPESP has essentially funding. The funding for FAPESP is legislated in the state government, and it is a proportion of the taxes that the state collects. It goes to the research organization, and because of that, you are only subject to variations in let's say the economy, right? Because if people buy less, they pay less taxes, and that has helped the universities in the state of São Paulo quite a lot, right? In particularly their research. Now, I would say that something we miss a bit when I go overseas, right? I don't see that many South Americas, Latin Americas in there. And I would like to have more, right? So I think there is a bit of a disconnection here because even though there's a lot of talent, they don't make their way through to the best research organizations, right? And I try to do my little bit of that, which is going to universities in South America, Latin America in general, giving talks and say, well, if the students are interested, this is how you can apply, right, for PhD degrees or for master degrees overseas and so on. We just need to make people more aware. I think that would help, and yeah, and we should all do a bit of our bits for that.
No, I 100% agree there. I've been, as I speak with different people from different research labs here, one of the common things they say is like when they have somebody from Latin America in the team is the quality is amazing. We just need to have more. So definitely, and one of the exciting points that we were speaking last week that for me was happy to hear was how you're starting to see kind of a growing number of Latin Americans going to this global conference on robotics and simulations.
Yeah, absolutely. Yeah, last week I was attending this conference called RSS, Robotics, Science and Systems, right? Is one of the main conferences in robotics. Two Brazilian students approached me in Portuguese, right? And say, oh, I'm a student from this university. I'm a student from this other university. We've been reading your work. We like what you do. How can you be in this position? What's your model? How should we follow, and so on, right? That was great to see. It was great to see more students now joining these top conferences, right? And if there is an advice for many of the Latin American students is to attend conferences, right? Go to conferences, and for my colleagues in South America, try to get the conferences in your countries, right? Have them there, right? So, for example, there is one, it's perhaps my first conference called Uncertainty in Artificial Intelligence, and it has maybe 30 years of history, and it's going to happen in Rio this July, in 2 weeks, right? So it's great to see. And one of the largest conferences in machine learning will happen in Rio later next year. It's called iClear, right? Is the conference on representation learning. These are thousands. I think the last iClear is about 10,000 people attending. And it's going to happen also in Rio. So we should have more of this because that's when the locals can go and interact with the world, and they will pick up what's going on very quickly, right? Once they are part of that environment.
And to finish, I would like to do a quick fire round. So I give you some 3 quick questions and you give me your 3 quick answers.
Sounds good. Let's go.
What's something you initially got wrong about generative AI over the past 2 years, and what that you have changed your mind about?
Yeah, I thought I could quickly ask generative AI how to decompose a task as simple as putting an apple inside a cabinet. And if I ask this task, very simple, to any of the generative AI models, let's say, at least until a few weeks ago, you would not give me that answer. So the answer should be, well, you open the cabinet, you pick the apple, put it there, and close it. But they don't work. They say, oh, you pick the apple, then you put the apple elsewhere, or you grab another arm, then you open the cabinet, then you put the apple inside, then you close the cabinet. So they still don't have that level of reasoning that I would like them to have. And I've been trying, and any of your listeners could try this. You are a robot, you have a single arm, there is an apple in front of you, and I would like to put this apple inside a cabinet. What sequence of actions or tasks should I do? Let's see what you get.
Yeah, no, I was also reading Anthropic did an experiment of letting Claude run a business, and it started selling the things for a lower price than it had bought. So definitely some exciting progress, but still a long ways to go. Do you think we will get a Waymo-like experience in several countries in Latin America within the next 15 years?
Or an autonomous car, such as Waymo?
Like SF, seeing many Waymos in the streets in Sao Paulo, Bogota, Santiago de Chile, with all the challenges and on different fronts that likely that you'll have.
Yeah. I think it's possible. I think it's possible. It's always, a matter of cost benefits and so on. And last week I rode the Waymo vehicle several times in LA. They were very smooth. I was super impressed with the behavior. So sometimes they would go over, potholes or things like that, right? So if I was a driver, I would try to avoid it, right? But for the majority of the rides, it was super smooth, right? So I think that can happen for sure.
No, it's going to be interesting. I know there are some having come from Latin America and the driving and some situations, streets, the simulation is going to be an interesting challenge. And the last one is, what timeline do you expect for the average household to have either a humanoid robot or multiple robots performing the majority of household tasks, called dishes, clothing, clothes folding? So it involves kind of 2 parts: being economically feasible for the average household to be able to have it, and the second part, and actually the robot being able to do it.
Yeah, I think if it is a humanoid trying to do all of these tasks, it will take longer, right? So I would say perhaps 15 years or so that it will become reliable and robust enough to do that. But for simpler, let's say, task-specific robots, just like you have your Roomba cleaning up the floor, you could have a robot that hangs, the arms are assembled in your kitchen, let's say hanging from the ceiling or something like that, right? And they would cook or, move the pans and do things like that automatically for you. So that, I think, it's doable, faster than having full humanoids. So I will put that, let's say, between 5 to 10 years.
No, and with that positive note, Fabio, thank you very much. Really enjoyed the conversation. Thank you for joining.
Thank you so much. This has been a pleasure and a lot of fun.
Thank you.